For decades, the name of the game in computing has been faster, faster, faster. But what if that's the wrong race entirely? What if the real breakthrough isn't about just cranking up the speed, but starting completely over? Today, we're diving into neuromorphic computing, a radical idea that rebuilds computers from the ground up, using the most powerful processor we know as a blueprint, the human brain.
So let me ask you something. What if our computers, the ones we use every day, had less in common with a calculator and way more in common with a brain? What if they could learn and process information with that same incredible efficiency? This isn't science fiction anymore. It's the core idea driving a huge shift in technology.
Okay, so you might be asking, why? Why do we even need this crazy new approach? Well, it's because our current computers, for all their amazing power, are hitting a wall, a really big one. And it's all because of a massive data traffic jam that's been building for decades.
Yeah, at the heart of this whole problem is something called the von Neumann bottleneck. Think about it. For over 70 years, we've built computers the same way. The processor, the brains of the operation, is over here, and the memory is way over there. Every single bit of data has to get shuttled back and forth on this tiny little highway. In today's world of giant AI models and big data, that's not just a bottleneck, it's a permanent, gridlocked traffic jam, and it's wasting a ton of energy and time.
So, what's the solution? Well, it's kind of obvious when you think about it. Stop separating them. And this is where the neuromorphic approach gets brilliant. It takes its blueprint directly from the brain, right? Because in our brains, processing and memory aren't these two separate things. They're woven together, they're fused. We call it in-memory computing, and it just completely gets rid of that bottleneck. Poof, gone.
But okay, solving the hardware problem, that's only half the story, right? If you build a computer that's shaped like a brain, you also need software that thinks like a brain. And that means we have to come up with completely new kinds of algorithms.
And that brings us to the absolute core concept here, spiking neural networks, or SNNs. Now, these are not like the AI you're probably used to, which just crunches continuous streams of data. Nope, SNNs are event-driven. They communicate using these tiny little electrical pulses, or spikes, which is almost exactly how the neurons in your own brain work. A neuron only fires, it only spikes when it has something important to say. And that tiny detail makes the whole system unbelievably efficient.
Here's a really good way to picture the difference. A traditional AI network, an ANN, it's like a continuous shout. Every single neuron is yelling all the time, processing data nonstop. It's powerful, for sure, but man is it loud, and it just guzzles energy. An SNN, on the other hand, is more like a super efficient Morse code. Neurons only tap out a little spike when there's new, important info. This sparse communication, that's the secret sauce. That's where all the magic efficiency comes from.
So, what's the payoff for designing things this way, for copying the brain? Well, it's just staggering. When you put this hardware and software together, you get these amazing systems, like Intel's Loihe chip. And these things can do really complex jobs while using up to 100 times less energy than the powerful CPUs and GPUs we rely on today. I mean, that's not a small improvement. That is a game-changing leap.
Okay, so we've got brain-like hardware, we've got brain-like software, we're all set, right? Well, not quite. This leads us to the biggest challenge of all. Building a brain is one thing, figuring out how to teach it, that is a whole different and way, way harder problem.
The most brain-like way to learn, it comes from this really famous idea: neurons that fire together wire together. It's this beautiful, simple, local rule. It basically means that if one neuron helps another one fire, the connection between them gets stronger. The question is, how do you turn that elegant idea into an actual algorithm?
Well, the answer is an algorithm called spike timing dependent plasticity, or STDP. This is basically the computer science version of fire together, wire together. It's all about timing. If an input spike shows up right before a neuron fires, boom, that connection gets stronger. If it shows up just after, it gets weaker. It's a simple local rule that lets the network figure out patterns all by itself, without a person telling it what's important. That's the unsupervised part. And you guessed it, it's crazy energy efficient.
And this really brings us to a fork in the road, two completely different philosophies on how to teach an AI. On one side, you've got that elegant, biologically plausible STDP we just talked about,
And on the other side, you have the heavyweight champion of traditional AI, back propagation through time, or BPT. Now, BPT is not at all how a brain works. It needs a ton of memory, but right now, it is absolutely unbeatable for getting super high accuracy on really tough jobs. And here is the big problem. BPTT, the gold standard for training our best AI models, is totally incompatible with neuromorphic hardware. It just fundamentally breaks the rules. See, to work, BPTT needs to store the state of every single neuron at every single point in time so it can go back and calculate errors. This demands massive amounts of memory and a step-by-step process, which completely wipes out the low-power in-memory advantages that make this brain-like architecture so special in the first place. So, what do you do if you can't use the best training method? Do you just give up? Of course not. Engineers came up with a really ingenious shortcut, a workaround, that tries to get you the best of both worlds. And this workaround is a pretty clever three-step process. First, you take a traditional AI network, an ANN, and you train it the old-fashioned way, using a powerful method like BPTT until it's super accurate. Then, step 2, you take all the knowledge it learned, all its weights and biases, and you basically copy and paste them over to a spiking neural network. And finally, step 3, you let the SNN run the show. It's now doing the job, what we call inference, with all the smarts of the original network, but with the unbelievable energy efficiency of the neuromorphic chip. But you knew there was a but coming, right? Of course there's a catch. This conversion process, it isn't free. When you go from the smooth, continuous numbers of an ANN to the simple on or off spikes of an SNN, you lose a little bit of precision. These are called quantization errors. And these tiny little errors, they can add up, layer after layer. To make up for it, the SNN often has to think for a little bit longer, run for more time steps to get to the right answer. And that extra time, that latency, can start to eat away at one of the key promises of this tech. So, with all these challenges, all these workarounds, is it actually worth all the trouble? Well, the results from real-world systems are finally starting to roll in, and they are showing us both the incredible payoff and the huge hurdles we still have to clear. And the scale of the payoff, it is just mind-blowing. Let's take IBM's North Pole chip, for example. When you put it to work running big AI models, it's not just a little bit better. It is almost 47 times faster and over 72 times more energy efficient than the best GPU you can compare it to. We're not talking about small incremental gains here. This is a whole new ballgame, a paradigm shift. Okay, but before we get too excited and declare victory, we need a serious reality check. As amazing as these chips are, when you compare them to the thing they're trying to copy, they are still profoundly inefficient. The human brain runs on the power of a dim light bulb, with an efficiency that is still at least 4 orders of magnitude. That's 10,000 times better than our best neuromorphic chips. We still have a long, long way to go. So what's really holding this tech back from being everywhere? Well, it boils down to 3 big hurdles. First, the software. The whole ecosystem is brand new, there aren't many standard tools, which makes it really hard for developers to get started. Second, you have to completely rethink your data. You need new tools, new pipelines, all built for this new event-based way of thinking. And finally, and this is the really big one, we have to stop trying to just jam old algorithms onto new hardware. We need to co-design brand new algorithms that are made from day one to work with this amazing hardware, not fight against it. Which really leaves us with this one fundamental question for the future of AI. The path to truly intelligent machines seems to be splitting in 2. Do we keep trying to perfect the brute force code-heavy approach that's gotten us this far? Or do we go all in on perfecting our copy of the brain, betting that after billions of years of evolution, nature's blueprint really is the ultimate key? The answer to that is probably going to define the next generation of computing itself.